Hi, I'm Prof L and welcome to Chemistry Matters, and today we are going to be talking about electrochemistry, and in particular a very important part of electrochemistry, how to essentially quantify what's going on in any redox reaction. So, if you recall in the last video, we looked at this thing here that is called an electrochemical cell or a galvanic cell, call it what you will, and we figured out what was going on in this. We said that we have got the flow of electrons from the anode to the cathode, in other words, from the zinc electrode to the copper electrode, and we know that there's a spontaneous flow of electrons happening there because we have got a potential difference between these two electrodes. Now, if you look at this, this says that the potential difference is 1.1 volts. And so the question that we're going to answer today is, how does that potential difference come about? How does that particular magnitude come about? Why is it 1.1 volts and not 0.3 volts or 2.4 volts or whatever? So we're going to be quantifying electrochemical cells today. Okay, so in order to do that, we're going to show you a little bit of shorthand to start off with. And rather than having to draw out this particular diagram every time we want to talk about a galvanic or an electrochemical cell, then what we would do is draw it in a particular shorthand which contains essentially all of the information that's in there and is much easier to use. Okay, so how do we do this? So what we've got happening here is we have got, at this particular electrode, we have got solid zinc going to zinc 2+, and at this particular electrode here, we've got copper 2+ going to copper. Okay, so those are our two, let's call them half equations, because that's essentially what they are. Okay, and so the shorthand way of writing this now is going to be this. We are going to take solid zinc, okay, and we're going to have a vertical line between it and zinc 2+, and then we are going to have a double dotted line, and then we are going to have over here copper 2+ and a solid line and copper, like so. So this here is the shorthand representation of our galvanic cell that we have here. Okay, so what does this all mean then? So what have we got? We have got vertical line, and a vertical line shows that you have got whatever on either side of that vertical line in different phases from each other. Okay, so here we've got zinc, solid zinc. Here we've got aqueous zinc 2+. Okay, so they are different phases, so we put a solid line between them. The double dotted line here refers to the fact that we've got a salt bridge, essentially, so that this left-hand side is separated from this right-hand side essentially by a salt bridge. Okay, and on the right-hand side, what have we got? We have got aqueous copper 2+ here, and that is a different phase from solid copper here, and so therefore we denote that with a solid line like so. Okay, so instead of having to draw out this whole thing, all that we need to do now is use this. Okay, so this shorthand diagram here. So a shorthand, what we call a cell diagram. Okay, now importantly, when we write a cell diagram, and this might seem blindingly obvious, but it's very important, this, the one that we have on the left hand, is the left hand electrode. Okay, and the one that we've got on the right hand is the right hand electrode. Okay, and we've already seen that if our electrochemical cell is spontaneous, this on the right hand is where we are going to get reduction, And this on the left hand is where we're going to get oxidation, okay? Now, that's only if the reaction is spontaneous, and we'll come back to that because this is where people do get a little bit confused in electrochemistry, okay? One more quick example of a cell diagram and what happens if your two species on one side of your cell diagram are in the same phase. Well, we simply separate them with a comma, okay? So in that case, we would go Fe3 plus, comma, Fe2 plus, like so, okay? So that's all of the terminology that you need to know for cell diagrams. So hopefully you can sort of look at a cell diagram now and figure out what is going to be happening. And in fact, in this particular cell diagram, you might ask, okay, well, these two are aqueous. What is your electrode made of? Good question, okay? So your electrode very probably would be made of some inert metal like platinum that doesn't get involved in the reaction itself. It just serves as a vehicle for the transport of electrons, okay? And because platinum is solid and these guys are aqueous, we would have a solid line there, but you would recognize that platinum is not doing anything. It's not involved in the redox equation. And we'll see that quite a few times, in fact, especially if you're looking at reactions of gases and stuff where you need a solid electrode. Okay, so that is your electrochemical cells. Now, okay, let's leave that there. And let's go back to this question of where does this 1.10 volts come from? Okay, what determines the value of the potential difference between those two electrodes? And so here is a very, very important equation. So the EMF of the cell, the potential difference of the cell, the voltage, call it what you will, okay, is defined as being the E of the right-hand electrode minus the E of the left-hand electrode, okay? And if we do all of this under standard conditions, then we can put in the standard sign there, that the E standard of an electrochemical cell is the E of the right-hand electrode minus the E of the left-hand electrode. Okay, that's great, fabulous. But we have a problem, don't we? Because what's happening at the right-hand electrode, for example? Okay, the thing that's happening at the right-hand electrode is we have got a reduction. Okay, we have got copper 2 plus and 2 electrons being reduced to copper. And that's it. Okay, that's happening by itself. Now think about that. Can you have a reduction occurring by itself? And the answer is no, you can't. In the same way that you can't just have an oxidation occurring by itself. Okay? Something doesn't just spontaneously lose electrons unless there's something else there to gain those electrons that have been lost. Okay? And again, if you just had, for example, a reduction occurring by itself, then very quickly you're going to lose your charge balance. And you've always got to have charge balance, okay? So if a reduction is occurring through something gaining electrons, where did those electrons come from? Okay, they must have come from an oxidation. So what I'm trying to get at here is how the heck do you measure a potential difference for a reduction or the potential difference of an oxidation occurring by itself? The simple answer is you can't. Okay, so if that's the case, how does this then make any sense? Well, we cheat a little bit, okay? And we are going to make this equation relative, okay? We are going to make this E standard, this E for a reduction relative. We're going to make this E for an oxidation. We're going to make it relative. And the thing to which we are going to make it relative is for the reduction of protons to hydrogen. Okay, a half H2 gas. So let's say that's aqueous. And here we have the reduction now of protons, H plus plus one electron, giving a half H2 gas. Okay, and we are going to, so this is a reduction, and we are arbitrarily going to say that E standard for that reduction, when it's carried out under standard conditions, when you've got 1 mole per litre of protons and you've got your H2 at 101.3 times 10 to the 5 pascals, sorry, 1.013 times 10 to the 5 pascals, in other words, yep. When you've got those conditions, E naught for that cell is equal to 0.00 volts. And notice I said cell, I meant to say half cell, because this is a half reaction. It's essentially half of an electrochemical cell. And now we are, as I say, arbitrarily saying that the E standard for this particular reduction reaction is 0.00 volts. And that's really important because once we arbitrarily assign that value, then we can measure, and like physically measure, the E standard for all other half reactions or half cells relative to this here. Okay? So shorthand for this is E naught of H plus H2. Okay? So that's essentially shorthand. So you'll see this defined in your notes and stuff like that. E naught of H plus H2 is equal to 0.00 volts. Right, knowing that, then let's figure out how we can use this to our advantage. How can we use this to then determine the E naught for any other half cell? Okay, so specifically, let's go back to, for example, copper. Okay, we talked last time, well, in this particular one here. Here's your copper 2+ reduction. Cu2 plus 2 electrons giving copper. How do we find E naught for that? Okay, so the way that you do it is you set up an electrochemical cell. And you set up an electrochemical cell like this. So H2, H plus, blank, salt bridge there, copper 2+, Cu. So we've got two half cells. We've got the overall electrochemical cell made up of two half cells. Here on the left-hand side is our, remember, oxidation. Oxidation occurs at the anode, the left-hand electrode. Here is our reduction. Reduction occurs at the right-hand electrode. Okay? So we said that E cell is equal to E of right hand minus E of the left hand. And again, to avoid confusion, let's put the standard there. Right. Now, what do we know in this equation? We know the E naught of the left hand because we've arbitrarily said this is going to be 0 volts. We don't know the E naught of the right hand. And we don't, at the moment, know the E naught of the cell. But hey, we can do an experiment. We can say, okay, let's actually set up a physical electrochemical cell that looks like this, and let's measure E naught for that cell under standard conditions. And when we do that, we do the experiment, we find that this then has a value of plus 0.34 volts. And that is equal to E of the right hand minus E of the left hand, and we already know that E of the left hand is 0. So in other words, E cell is equal to the E right hand minus E of the left hand, which is 0. So therefore, E of copper 2+ copper is equal to plus 0.34 volts. And now what you have is the E naught value for a half cell, for a half reaction, for a reduction by itself. And again, remember, we're cheating just a bit by arbitrarily saying that the E naught for this here, hydrogen going to H plus, is equal to 0 volts. Okay. So, what does that then tell us chemically? Because remember, we don't just do this for for fun. We want to know what's going on. So what that is saying is that if we do set up this electrochemical cell, it's going to have a positive value of E naught. And if that's the case, that means that yes, reduction does occur here, oxidation does occur here, and the whole thing is spontaneous. And so therefore, what is happening in this particular case, what we're saying is that copper 2 plus is going to oxidize H2 to H plus and get reduced to copper under these particular conditions, okay? So, very, very important, very, very fundamental stuff, this. And I think I was going to talk to you more, but this video is getting a bit long as it is at the moment. So we will talk about the ramifications of all of this in the next video. And so stay tuned for that, I guess, and we will see you soon. See you later.